Hello, hello. Thanks for inviting us, given the BioCosm stage. This talk is written for this stage. We'll start with a little performance by Reinis, but I guess he needs a bit of time to get ready, so I'll spend it talking now. So I've been working with space technology for more than 12 years in the S-Cube project, in Comet Interceptor, and this is a kind of a hobby project that we do under the Space Travel blog. And now we've been recently performing several times with Reinis together. And I have these slides ready, which are amazing images of the universe, and some of them taken by European Space Agency. And then Reinis will improvise on top of that. And when I say improvise, I'm not really sure what's going to happen in the background, but the main point is that your mind will be hopefully entertained by me a bit, and then your soul will be entertained by Reinis. How are you doing, Reinis? history of the universe spans 13.8 billion years. It includes everything we know, see, and experience. And I've been fascinated by this cosmic universal story about where we come from, meaning of where the stuff comes from, who we are, and also where we come as a life form. And well, we're given so much time, I will need to skip over some of the parts of this talk, so I hope you familiarize yourself with this cosmic calendar where we take a period of 13.8 billion years and squeeze it into one calendar year, where we have the early universe in January, and then our Milky Way galaxy develops in May, and our own solar system develops in September, and soon after we have increasingly complex life forms developing on the Earth. And only later in December, or in the second part of December, we see life forms that we are used to seeing and we are used to being. And what we know from the human history, that's only the last few minutes, or our recorded history is only the last minute. With this, we want to show that the time when we are here on the planet Earth is really short if we compare it with the age of the universe or with the age of the solar system. Now, how it all started, the universe was a rather odd moment. The leading cosmological theory that it all started with a Big Bang, as you know from the series. And what it means that everything, all the stuff that's in the universe was somehow packed in an infinitely small place with an infinitely large density. That's a place where known laws of physics do not apply, but this model explains that our universe is expanding. And here in this image, you can see some of the early phenomena when we have the first atoms forming in the universe, and from there on we can, the universe can create its stars, and those stars go in, make up galaxies. And around stars we also have planets and the moons and so on. As scientists, we are of course interested to image or to somehow measure the universe. And this is so-called microwave background. It is the oldest image of the universe we can take. And here you can see just a fraction of degree differences in temperature in the early universe, which is like the hotter places are represented with the red color, and then it goes to the blue color, which are cooler places. And what is surprising from this big image is that the places where the temperature was a bit higher, that is the places where the large-scale structure of the universe formed. Now, we can only imagine how the first stars were formed, and this is an artistic impression, but what we can measure and model is the large-scale structure of the universe, which you can see in this beautiful simulation. maybe I should just let Reinis continue, but we have some traveling to do. We're quickly going from the large-scale structure of the universe, which includes a lot of cosmological structures. I'm skipping over here, and we're very fast moving to our closest galactic neighbor. So this is Andromeda galaxy, 2.5 million years from us, 2.5 million light years from us, and it's so close that actually this image is taken by an amateur astronomer with a telescope. Probably you could afford as well. So yeah, the space is really close. Now, but if you look deeper and deeper in space with better and better telescopes, if you look for longer time, which is more exposure time, then it's like traveling back in time. And here you can see the Hubble deep field, which was not made in the 90s for the first time, and they were observing some patch of sky which seemed to be just empty, and they found out many new galaxies, and at that time those were some of the most oldest known. So that one image already provided us with a way to travel in time. Now, what else is there in the universe? We know that around the sun we have planets, and it seems logical that there are planets around other stars as well, but that wasn't known that well until 90s, when so-called exoplanets were started to be discovered. And by now we know that in the Milky Way galaxy there is on average about one exoplanet. There's about one exoplanet per star. And again, this is new knowledge, and only recently this field is emerging where we start to characterize and see how these exoplanets look. And the one you saw there was just an artist's impression, pretty much. Now, our own galaxy, the Milky Way, we don't even need any special equipment to see. We can just go out in a Tsana bog, escape the light pollution, and see it for ourselves. It's, I guess, one of the most beautiful things to see in our sky. And now we are arriving at our home star, the Sun. And here you can see another artist's impression where they try to show the so-called accretion, when from the cloud of interstellar gas and dust and molecules, they collapse into creating the sun, and also there's leftover material that is formed into a disk, and in this disk the planetary formation happens. And the early solar system was a rather messy place, so planets, planetesimals, asteroids, comets, they were bouncing into each other, and we'll see some of that later. And then Jupiter came to help and cleaned up the system. And then now it's a much nicer place, except for the main asteroid belt, where you can still see the ancient asteroids tumbling around. Now, the history of the Earth is about the same as the history of the solar system. So the planets form very fast when the solar system itself formed. So it's about 4.5 billion years old. And here you can see, similarly as we had a cosmological calendar, this is a geologic clock. So in this 12-hour clock we can see some of the most important events that happen on the Earth. Again, we have to save a bit of time here. Just want to point out the main things there, that about 500 million years in the Earth history, the first life forms showed up. So we think that it is, at least for the conditions that we had on the Earth, it was rather likely that life will form. And we will see later that conditions conditions back then were not nearly as good as we have now, or as we think now. We have these, prokaryotes, early life forms, and they start to develop photosynthetic capability there around 4 o'clock, so around 3 billion years in the history. And this is over time evolved and evolved until there was the thing called, I really love the name, the Great Oxidation Event around the middle of the Earth history. So we had this atmosphere that was packed with greenhouse gases. You heard a lot about them in recent years, definitely. So that Earth was packed with those back then. But then with the photosynthetic capabilities, bacteria was able to populate the Earth atmosphere with the oxygen. And this in turn was amazing for eukaryotes because they thrive in oxygen. Meanwhile, they were not able to do it in the previous CO2-rich atmosphere. And then there were more complex life forms developing at the end. And yeah, we have a whole YouTube video on this, so you can watch that. Now we'll move a bit faster. So this is a molten lava ball, basically. An artist's impression of how the Earth might have looked soon after it formed. So basically, due to gravity, all these interplanetary gas and dust clumped together, and when there was enough mass, it all melted together. So there was rock and metals melted all together, and it's still, we know that the Earth has this lava core. And what is important in these moments is that these metal elements are creating our geomagnetic field. And here we start to move into this discussion into what makes the conditions on life so nice that we can exist here, because as you have heard many times in this today, that preparing stuff for space is rather complicated, and a human space flight is something that no one is talking about in Latvia, for example. But anyway, on the Earth we have the geomagnetic field, and it protects us from the solar wind, just to name one thing where it's amazing for life. Here you can see a simulation of the solar wind coming in from the right and encountering the Earth geomagnetic field. Simulations made by our colleagues in the University of Helsinki in a very high quality computer simulation, and this is amazing, the structure creating there. Right, I mentioned to you that the early solar system was a messy place, and it was a bit dangerous because it might as well have happened that in the Earth there was another smaller planet bouncing into it that people call Theia, but it's a hypothetical thing. And out of this impact, there was we had the creation of the Moon. And Moon is our companion. It guides us through the darkest moments. But what it also does on kind of geological scale is that it serves as a balancing swing, so to say. Basically, thanks to the Moon's presence, the rotational axis of the Earth became stable, we believe, and that helps us to have stable seasons, and life forms tend to like that. Now this looks like some other planet, but we're still talking about Earth as in terms of early Earth, so first billion years. And here we want to the main point we want to make is that it was a hot place where if there was any surface water, it would immediately evaporate. And the question arises where the water on the Earth comes from if the early Earth could not support it. Now here, European Space Agency is helping us a lot because they worked very hard to send the Rosetta probe to 67P and to check out how is the water on comets doing. And they found out that the water on comets is it has more heavy hydrogen. I don't know if that makes sense, but it's basically the ratio of this heavy hydrogen does not match that on the Earth. And we believe that this 67P is also similar to other comets. So in order to look for how the water came to Earth, we should look someplace else. And the less obvious place is asteroids. So we think they are dry and boring, but actually if we send instruments to Ceres that are able to see somehow what happens under surface, then we find a massive undersurface ocean under Ceres surface. So it's a large volume of water, and just if there are big asteroids like that, they might have brought most of the water on the Earth. Okay, so what else is super important here is that we have oxygen arriving in the Earth's atmosphere, and by now our I don't know, microbiology has advanced so far that we can develop these cyanobacterial mats and take images of them creating oxygen. So these are the types of processes that slowly, you know, drop by drop, we're creating oxygen in the atmosphere and creating the modern atmosphere that we know of today. And we start to talk about life here. We could quickly jump to this interesting animal, which is a fish, Tiktaalik fish, if I remember correctly. And these are the first evidences during the so-called Cambrian explosion, where we had mostly animals living in water, and then we have to explain how did they get out of this water, basically. So there's a rapid, over 20 million years, which is a very short period of time, there's a rapid development of, for fish, we would call them fins nowadays, but basically parts of the bodies that help them to grow extremities and help them to get out of the water. I would like to move back closer to time now and take some bigger steps here and show some witnesses of time, so to say. A couple of years ago I was in Sietinjezis, and this is a 4 million years old sandstorm formation. So 400 million years old, right here in Latvia, and only 200 million years. All the continents were joined into one supercontinent called Pangaea. So think that Sietinjezis was moving all along with the continents and is still there. You can visit it. Now this is a 160 million years old formation, the Delicate Arch in the US. And 66 million years ago there was possibly a impact on Earth, due to which a lot of the life was affected, and the biggest maybe sacrifice that the Earth made was the dinosaurs. That in that form we don't know them anymore, so they are extinct. We only see them in the archaeological track record. So this shows that the life on Earth can thrive, and then some conditions change and it goes extinct. And actually it's believed that this is not the only extinction event on the Earth. Now, so much about extinction. Let's talk about the formation of life. And there's actually not much to say about it, because we don't really know how life started on the Earth. And we cannot recreate this process in the lab as of now. But we know that the life forms can thrive in extreme environments. Here you can see an underwater thermal vent where there's high temperature, like, I don't know, 180 degrees, and there's no oxygen pretty much, but there are simple life forms living there. And these conditions actually are kind of similar what we have in the early Earth. So there might as well be these life forms surviving throughout different stages of Earth changing, and they find their own environments where they can thrive. And then we have this guy, tardigrade, which has been famous among scientists because they have tried to bring it to space, so where it is in vacuum and where it is in UV radiation, under ocean for several kilometers, and put in high and low temperatures in mountains. And many times, in most of these cases, these guys can survive. They kind of go into hibernation, and they can get through very rough times. And this shows that the life, as we see, as a very fragile and so on, it's not really a universal case. So what are the requirements for life as we know it to be? We think we need some kind of energy, and we mostly think of it as solar energy, but it can be thermal energy. For the life that we can study, we need water and carbon elements, and we also need some kind of exchange in nutrition. At the end of the day, we also need stable environment, because if our seasons would be too extreme, or every decade there is some big change in the weather, then this is not good for life, of course. All right, what's next? Now we quickly jump to the last 2 million years. We are here on Earth, and we have some apes that start to walk upright, and they start to develop bigger brains, and eventually they become Homo sapiens that dominate and basically are now ruling the planet. Yeah, that's all very recent. And what is even more recent is the last ice age. So if you look closely on the top, you can see that the Northern Europe is all covered with ice, and that is only some 11 to 15,000 years ago. So from the perspective of the geological history or the cosmic history, so this is nothing. Very, very, very last moments in our history. But then when the Ice Age was ending, so it uncovered new territories there in Northern Europe, and we were able to basically move there, and they were rich with forests, with nutritions, you know, with wildlife and so on. And you can see it in a lot of places still in its natural form. Around the same time, not necessarily connected, but maybe, we have the development of agricultural revolution, so let's say 11,000 years ago. And this is something that, so people from basically being kind of roaming around the planet or their own territory, they became fixed in one place, they started to do agriculture, and in a way they started to owe plants, and the plants started to owe them because they could not move around. Now another quick jump is the scientific revolution. We have development of modern physics, modern mathematics, scientific method. We are rethinking our structure of the solar system, as well as we are starting to build the first telescopes. So we, as a humankind, only a couple of centuries later, someone starts to think, hey, maybe we can do some economic theory on that. This is Adam Smith. He starts to write his most significant works in just 18th century. And then in 19th century, the Industrial Revolution is going full steam. And full steam it's going and it's leaving its traces. So since the Industrial Revolution started, we have the increase in the global temperatures. And this is, you know, done by these apes that started to walk upright and all that. And it's a space conference. I don't have to tell you how bad it is, because we can see it on other planets, and we can see it in the different times of the history of the Earth. And I think that the Earth, you know, it will be just fine. We saw different stages of the Earth. It survived. What is worrisome here is that the life forms on Earth, the diversity of life forms and the habitats, they are now being reduced and impacted radically. So, as a scientist, if I go to a bog in Kemeri, for example, then I think what to do next. So, what is our big, you know, roadmap? And I think the first item on the agenda is that Earth is an amazing place. We like to be here, it's comfortable, and thus far we don't have means to get anywhere else. So we should do our best to make Earth habitable and keep it habitable. And also it's scientifically very interesting to research how the life started, evolution of life, and maybe we can start to understand whether we can recreate it and how it survives in some different conditions. And last but not least, you know, human spaceflight, humans on the moon, maybe it's not that far distant future. So we should try to think, do we have alternatives to the Earth? Because if not for our own activities, then our evolution of the solar system or of our galaxy might require us to move someplace else. Thanks a lot.
Reinis, Andris, thank you for this very creative and immersive story.